In this video, we're going to revise the properties of quadrilaterals. The properties of quadrilaterals can be divided into three groups: sides, angles, and diagonals. The definition of a parallelogram is a quadrilateral that has two pairs of opposite sides that are parallel, and then these two same pairs will also be equal in length. A parallelogram's two pairs of opposite angles are also equal in size. Next, focusing on our diagonals, the diagonals of a parallelogram bisect each other. That means their points of intersection divides each diagonal into two equal parts. A rectangle, rhombus, and square are all also parallelograms, but specialized parallelograms with extra properties. All the properties mentioned above are then also true for these figures. For a parallelogram to now be a rectangle as well, it has two extra properties. The first of these properties is that all the angles are now 90 degrees. And the second property is that the diagonals are equal in length. For a parallelogram to be a rhombus, it also has a few extra properties, and the first of these is that the adjacent sides are now equal, which means all sides are equal. Then the diagonals intersect at 90 degrees, and the diagonals also bisect all the angles. Moving on to a square is then a parallelogram, which is also a rectangle, meaning that all the angles are 90 degrees and the diagonals are equal in length, and it is a rhombus. So all the sides are equal, the diagonals intersect at 90 degrees, and they bisect all the angles. This means that each smaller angle in a square is 45 degrees. It is important to notice that not all parallelograms are necessarily squares, but all squares are parallelograms with the properties of a rectangle as well as a rhombus. Our final two quadrilaterals are not parallelograms. The trapezium has only one property, and that is that one pair of opposite sides are parallel. A kite has no parallel sides, but there are two pairs of adjacent sides that are equal in length. Then there's one pair of opposite angles that are equal. And when looking at our diagonals, only one of them is bisected by the other, and that same diagonal bisects the angles as well. And lastly, the diagonals intersect at 90 degrees. Let's go and have a look at examples of how these properties can be used to determine the length of sides and the size of angles. Example 1. Rectangle ABCD is given with AB 50 millimeters, BC 120 millimeters, and angle C1 30 degrees. Calculate the length of AC. Because this is given as a rectangle, we know that the pairs of opposite sides are equal in length and parallel, and we know that all the angles are 90 degrees and the diagonals are equal in length. The 90-degree angle at B then forms part of a right-angled triangle, which means we can use the theorem of Pythagoras to determine the length of AC. However, before we can use the theorem of Pythagoras, we need to state that the whole angle B is 90 degrees because of the angles of a rectangle. Now we can state that AC squared, which is our hypotenuse, will be the sum of the other two sides' squares. And the reason for this is Pythagoras. 50 squared plus 120 squared will then give us 16,900. And to determine the length of AC, we take the square root of this value, and that means that AC is 130 millimeters. Question 2. Give the size of angle A1. Remember that we know the opposite sides of our rectangle are parallel, and therefore we can use alternate angles to say that angle A1 is also 30 degrees like angle C1. So I'm going to start off stating that BC is parallel to AD because they are the opposite sides of a rectangle. Next, we can say that angle A1 is then also 30 degrees because of our alternate angles with these specific parallel lines. Question 3. Give the size of angle D2. This angle will also be 30 degrees. And the reason for that is that we know that the diagonals of a rectangle are equal in length, and we know that the diagonals of a parallelogram bisect each other, forming 4 equal line segments. This then means that triangle EAD forms an isosceles triangle, and that is why angle A1 is then equal to angle D2, and they are both 30 degrees. And here my reason will be angles opposite equal sides. Example 2. In triangle ABC, angle A is 80 degrees and angle C 35 degrees. Determine the size of the interior angles of parallelogram BNEM. We can start off by determining the size of angle B, because angle B forms part of triangle ABC's interior angles. Therefore, B is 180 degrees minus the other two angles, the 80 degrees at A and the 35 degrees at C. The reason for this will be interior angles of a triangle, and then B will be 65 degrees. Now we can focus on our parallelogram, and because we know that the opposite angles of a parallelogram are equal, we know that angle B and angle E2 will be the same size, and therefore angle E2 is also 65 degrees. The reason we need to supply is opposite angles of a parallelogram. In a parallelogram, we also know that the pairs of opposite sides are parallel. Therefore, we can make use of the U to say that angle B plus angle M2 should equal 180 degrees. So we know that ME is parallel to BN because they are opposite sides of a parallelogram, and this means that angle M2 will be equal to 180 degrees minus the 65 degrees of angle B because of our co-interior angles with these specific parallel lines. So angle M2 is 115 degrees. And again, because we know the opposite angles of a parallelogram are equal, we can say that angle N1 will be the same as angle M2, so therefore also 115 degrees with our reason opposite angles of a parallelogram.